Right then, hello, welcome back. So this is the second part of the Universe Year 11 triple booklet. We've already looked at what the universe is, how big the universe is, the fact that galaxies are moving away from each other at high speed, and it would appear that the further the galaxy is away from us, the faster it is moving away from us. That's all to do with the Hubble constant, and if you double the distance that the galaxy is away from us, then you double the velocity it's moving away from us. So in actual fact, the universe is expanding at an accelerating rate, if you think about it. And now we move on to, well, do you know, how did Hubble actually, and other astronomers, how did they measure the speed at which galaxies are moving away from us? Well, we're going to start looking at light. So, this chap, Isaac Newton, there he is, first realised that prisms were good at splitting up white light into the colours of the rainbow. Roy G. Biv. Red, orange, yellow, green, blue, indigo and violet. Now what you do need to know about this set of individual colours of the rainbow is that they've got, although they travel at the same speed in a vacuum, they all travel at 300,000 kilometres a second, speed of light. They do have different wavelengths. Red having the longest wavelength. Violet having a much shorter wavelength. Remember, a wavelength is the distance between a peak and a peak, or a trough and a trough. You can see there that the red end is a much longer wavelength. Now, white light can be split up into Roy G. Biv. However, this person here, Joseph von Fraunhofer, discovered that the white light from the sun has got hundreds of tiny black lines in them, and you can see there's quite a few there over here, hundreds of these sort of black lines, where that particular wavelength of light didn't make it through to planet Earth, and there's a reason for that, as we'll come on to in a moment. They're called spectral lines. Now, in order to understand spectral lines which absorb light, we first have to look at different elements emitting light. Now, we're burning some hydrogen gas. It is giving off light. That light is made up of 4 wavelengths of light. This particular violet, 410 nanometers, bluey violet, bluey green, and red light of a wavelength of 656.2 nanometers. Okay, So this hydrogen gas is emitting light, and by using a prism we are able to split that light up into its constituent parts, the 4 wavelengths that make up this light here. It's called an emission spectra. This light here is emitting, giving off 4 different wavelengths of light. Now, we could do exactly the same thing with a tube containing hydrogen gas that is heated up. Once again, it emits light, it passes through a small slit, it then is split up using a prism, and once again, because it is hydrogen gas, it emits only those 4 characteristic wavelengths of light. We've got the violet one, we've got the bluey violet one, we've got the blue green one, and we've got the red one. Boom. Now it says here, complete the emission spectra for number 2, a light source that only emits light as a result of heating of hydrogen gas. So let's have a look at the first one. That is violet light. It's got a wavelength of 410.0 nanometers. Now, in order to put, you do need to know your powers of 10. So that would equal 410. Go back to the front of the booklet. You will find that nano is represented by 10 to the minus 9. Don't forget the units. We are looking at meters. So 410 nanometers actually is 410 times 10 to the 9 meters. If you were to put that into your calculator, you will get this value here. 10 to the minus 1, minus 2, minus 3, minus 4, minus 5, minus 6. Okay. All of those 3 values are the same. Here we see the emission spectra for hydrogen. In actual fact, it gives off 1, 2, 3, 4, 5, 6, 7, 8 different wavelengths of light. Sodium, it would appear, only gives off 2 specific wavelengths of light. Helium, several, and neon appears to be mostly in the longer end of the spectrum. The wavelength is longest. This is the shortest down here. So, this chap, Kirchhoff, discovered that hydrogen, the light from hydrogen, is sent through a slit. A prism causes the wavelengths of light to be split up into all its specific wavelengths. And then if you were to pass those specific wavelengths of light through hydrogen gas, and this bottle contains hydrogen gas, all of those wavelengths of light would be absorbed and redirected in other directions. Effectively, none of the light would get through. So the resulting spectrum that you would see is nothing. none of those wavelengths of light would get through. Let's just go through this again now. A light bulb emits white light. It passes through a slit, and using a prism it is split up into the colours of the rainbow. Roy G. Biv. Nice and simple. If you send that white light that contains all the Roy G. Biv through hydrogen gas, pass it through a slit, and cause that light to be split up using a prism, then you get Roy G. Biv again, but the hydrogen gas has absorbed its specific wavelengths of light, specific to hydrogen. So what we have now is an absorption spectra. We've got those spectral lines there. It's been absorbed by the hydrogen gas. Now, if we take light from the sun and pass it through a slit, and then pass it through a prism, and we get this result here, which is exactly the same as the one above. This is suggesting that the atmosphere, the gas cloud that surrounds the sun, has once again, like the bottle of hydrogen gas, it has absorbed certain wavelengths of light, which correspond to hydrogen gas. So the gas cloud must contain H, hydrogen. So this is a way of working out what the elements are in the gas cloud or atmosphere of a star. Even though we're nowhere near that star, because of the absorption spectra that has been given off, we can state that that gas cloud contains hydrogen gas. Now, the absorption spectra shows the spectral lines. They are caused by gas atoms contained within the sun, absorbing light of certain wavelengths and then re-emitting them in all directions, showing these spectral lines. This allows us to say what elements are contained within the sun itself. These just go through exactly what I've just gone through before. Okay. Sir Norman Lockyer. Looked at a solar flare during an eclipse and found a yellow line that corresponds to this wavelength here, 588 nanometers, or 5.88 times 10 to the minus 7 meters. At the time, no known element produce this spectral line with this colour and wavelength. Lockyer suggested that this line corresponds to a new element. He called it helium, after the Greek word for helios, meaning the sun. Why is produced by helium gas? What type of spectra is this? That type of spectrum is an emission spectra. Add in the spectral line into spectra X that would be created as sunlight passed through the helium gas. Well, as sunlight passed through the helium gas, this wavelength of light would be absorbed. So what type of spectra is X now? It's an absorption spectra. Question 4. What is an absorption spectra and how can it be used to explain the chemical makeup of stars and galaxies? Well, gas atoms absorb sunlight, or the light from galaxies, of a certain wavelength. That's a symbol for a wavelength, upside down Y. They then re-emit them in all directions. So those wavelengths of light are absorbed and then emitted in all directions. So they don't reach your eyes, in other words. So these create all those black spectral lines. Remember, the position of these lines links to the elements that make up stars and galaxies. So the spectral lines tell us what the elements that make up stars and galaxies actually are. Now this spectroscopy, the use of wavelengths of light, we discovered that the spectral lines of these stars could be shifted towards the red end of the spectrum. The patterns always stayed the same. You can see that the patterns are the same here. Look at these double ones here and double ones here. And then the difference here and here and here is exactly the same as here and here and here. It's just they seem to have been shifted over to the red end of the spectrum in some stars. Now, why was this? Light waves emitted from stars and galaxies that are moving away from us appear to stretch. Their wavelengths get longer. There's something called blue shift. Blue shift, if something is moving towards you at high speed, then the wavelengths appear to get closer and closer the light will show a blue shift. Their wavelength has decreased. Their frequency seems to have increased, of course, because they're closer together. Now, we've got three objects here, bulbs. Here, the wavelength remains the same, so the object is not moving. Here, the wavelength is being stretched, so we're showing redshift. Here, the object is moving towards us, so the wavelength appears to be shorter, so we show blue shift here. Now, spectral lines. White light contains Roy G. Biv. Boom. We know that elements in stars absorb certain wavelengths of light. So I'm going to put some in. This is all the hydrogen and the helium and everything that makes up the stars. So that's the light that we get from, let's say, our sun. From close stars, because those stars are moving away from us at high speed, the elements are the same, but their wavelength appears to have been shifted towards the red end. So now what we get is these first two moving towards the red end of the spectrum. The single, and the single almost goes off the chart. Galaxies that are far away, galaxies show an even greater redshift. So these two, the doubles are over here, that single is here, and that other single has been lost from the visible side of the spectrum. Spectral lines. What is redshift? What is redshift? Answer. Boom. What's the difference between Fizeau and Hubble's explanation of redshift? Well, Fizeau thought that stars and galaxies were moving away from each other at high speed, which seems a reasonable explanation. Hubble went further, in actual fact. Hubble said, do you know what? These stars and galaxies aren't actually moving away from each other at high speed. It is the space in between them that is expanding. That's why we see redshift. Why do the furthest galaxies show the largest redshift? Well, the furthest galaxies must be travelling the quickest and show the largest apparent stretching of light and the largest amount of redshift. Which galaxy here shows the largest redshift? It's Galaxy S. How can you tell that? Well, look at this double line here. It's further towards the red end of the spectrum. So that galaxy is further away from us because it's moving at an apparently higher speed and its wavelengths have increased. Now, a model universe. We've got a balloon. We've got galaxies. What is good about this model? Well, as you start blowing up the model, the wavelength of light increases, and the space between the galaxies starts to grow. Where did this model break down? Well, the galaxies themselves appear to increase in size. This doesn't happen in reality because gravity holds them together. Plus the fact the amplitude of the wave appears to increase as well, which is incorrect. How could we improve this model? Well, instead of drawing little dots to represent the galaxies, you would stick small dots of paper onto the balloon to represent the galaxies. Cosmological redshift is one piece of evidence for the Big Bang theory. But there's another one. Cosmic microwave background radiation. What is this all about? Well, the Big Bang released time, space, matter, and energy into the universe. This energy was released as gamma waves, part of the electromagnetic spectrum, a very, very, very small wavelength. Over time, redshift caused these gamma waves to increase in wavelength, passing from gamma waves into X-rays, passing from X-rays into UV, then into visible light. So the universe must have been bathed in visible light for some time. Then infrared, and then finally cosmic background microwave radiation, so microwaves. And they were spotted by these two individuals, Panzias and Wilson. They had a detector, and wherever they put that detector up in the sky, they could hear these background microwave radiation. It was the remnants of the Big Bang explosion, when all of that gamma radiation was first released. This is a map that represents small changes in intensity of cosmic microwave background radiation. High density here, lower density regions here. Without these small changes, matter would not have clumped together to form the stars and galaxies, so it was necessary for our universe to be created. We're almost at the end, but not quite. The Big Bang is an amazing theory. First proposed by George Lemaitre in 1927. What makes it such a good theory is its basis in observation and evidence. Without cosmological redshift and cosmic microwave background radiation, the Big Bang theory would only be that, a theory. The theory does have its problems. There doesn't seem to be enough matter in the universe to back this theory up. How is our universe going to end? Well, don't worry, it ain't going to end too soon, but there are 3 ways that our universe could go. all I'm trying to do is get a pen. There we go. Right. How's it all going to end? Well, we could, with time, see the universe stop increasing in size and turning into a final volume. So this is a final volume universe, where the explosive force from the Big Bang is balanced by gravity, all nice and static. We could have, theory number 2, ever expanding universe, which would be a little bit dull because eventually every object would move away from every other object and you wouldn't see any stars or galaxies in the sky. Here, the explosive force from the Big Bang is greater than gravity. But what if gravity wins? Well, at the moment we're in an expanding universe, and then if gravity won and everything was brought together, everything will get very, very close, very, very hot, very, very dense, and then very, very not alive. Could it be that we come back to a situation where the whole process of the universe restarts? Who knows? Hope you've enjoyed it. See you soon.